All right, we're talking about slope fields today, and they look a lot scarier than they really are. Basically, a slope field is just a graphical representation of a set of slopes obtained from a differential equation. So basically, the idea is it's giving you a visual of what the slopes look like for any general solution of any function. Okay, so sometimes you can't integrate because you can't separate the variables, but you can use differential equation to plot the slopes for the function and just get a good idea what the functions look like. So here in example 1 we have, it says that our derivative equals negative x over y, and we need to figure out what is the slope at each of these points on the function, right? So at the point negative 3, 2, the slope, at the point 3, 2, the slope would be negative 3 over 2, right? Because it's negative x over y. At the point negative 1, negative 3, it'd be negative 1 over 3, which is positive 1, so 1/3. Negative 2 over negative 1, so that makes a positive 2 on top. Wow, that is really ugly. Okay, that makes a positive 2 on top, and a negative 1 still on bottom, so that's going to be negative 2. And then the last one, if we had negative 2 over negative 2, that is going to give us 1. Okay, so those are the slopes of this function at each point. We don't know what the function actually looks like yet, or what the function is, but we can find its slopes from the differential equation. So why can't you find slopes when y equals 0? Well, that one hopefully is a little bit obvious, because if you look at the function, y is on the bottom in the denominator, and we can't have 0 in our denominator, so this function is not going to have defined slopes at y equals 0, at any of y equals 0. So what we're going to do is we're going to actually plot these slopes of this differential equation, and it's already plotted, our book has already plotted some of them for us. And so if you look at the first one, or at this graph, you notice, hopefully you notice that there's no slopes plotted here at y equals 0, because this function does not have defined slopes at y equals 0. So it just doesn't have defined slopes there. So we're not going to have any slopes there, but we're going to look everywhere else. So what I like to do is make a little table. Okay, x, y, and then this is going to be dy dx. Okay, so I start by looking at the different points that I need to plot and finding out what their slope is. So the first point I have here is this one right here. It's at negative 1, positive 1, negative 1, 1. And so what is the slope at that point? Well, if I put negative 1 over 1, I would just get 1. So the slope at that point is 1. So I'm going to try to graph that slope. And this one's, it's a little hard to see, so maybe I'm going to draw a line that has a slope of 1 because it goes through, goes up 1 over 1. And so then I'm just going to draw it at about that. Just a little dash mark that's got a slope of 1. So it's just a visual of what that slope actually looks like at that point. Okay, so let's move over to the left one. So we have negative 2, 1. Well, that would be 2 over 1, right? Because negative 2 over positive 1 is going to give us a positive 2. So, I've got all these written down here. So we're going to have positive 2 here. So again, I could draw this line. Maybe I have a line tool here that goes through those points, and then I could draw like a little dash, maybe. And then, can I erase? No. Well, that didn't help me at all. Now, did it? Ah! Haha! Okay, that was a little bit roundabout. We're probably not going to do that. But you draw a line that has a slope of 2, and then you just, do a little dash that side. Okay, let's go to the next one. So negative 3, 1, that's going to have a slope of 3. And so again, you draw a line that has a slope of 3, so up 3 over 1, that's going to be something like that. It's going to have a pretty steep slope, and so then you can draw a dash that is about that slope, and there you go. Okay, so we're getting like a visual of what this function is maybe going to look like, and then let's just keep picking points. We're going to pick the point, what is that? Negative 3, 2. Negative 3, 2. That's going to have a slope of 3/2. So it's not going to have a slope nearly as steep as the one below it. It's going to be about 1.5. So, you know, I know that this is really hard for you guys because it's not precise. You know, it's not like super, like just exact, and that is hard. So you'll get used to it. Okay, so let's make another, let's try some more. Okay, so if we have the number, let's see, 1, 2, 1, 2, then we're going to have a slope of negative 1/2. So we're going to have a negative slope here, but it's going to be really shallow, so like that. And then if we have 2, 2, which is right next to it, we're going to have a slope of negative 2 over 2, which is negative 1. So that one's going to be a little steeper. And then above it, we've got 1, 3. That's going to be a negative 1/3. And then next to that, we have 2, 3, which is negative 2/3. Okay, so this one's going to be a really shallow slope. Really shallow. And then that one's going to be just slightly less shallow, but not quite a 1. Right? And then what if we have 3, 3? That's going to be negative 1. So, negative 1. And what I forgot to mention actually, and this is a good way to do it, is to look for patterns. So you see here, when x and y are equal to each other, we have a slope of 1 or negative 1, right? Because this would be negative 1 over 1, this would be negative 2 over 2, this would be negative 3 over 3. And so when x and y are equal to each other, here at 1, 1, 2, 2, 3, 3, they each have a slope of 1. So now we can come down here and we can look at this one down here. This one should have a slope of 1, right? Because it's 3, negative 3. And then they already have the other ones. That pattern is already kind of filled in there. So you have those ones because they all are equal to that. And then you can look at maybe when, when are they equal to 1/2? Well, that's when x is half of y. So we've got like when x equals 1, y equals 2, and I guess we don't go out to 4. But you can start seeing patterns, and then you don't have to do the entire table every time. So let's take a look here. Let's get negative 1, negative 2 is going to be negative 1/2. Okay, so it's going to have a negative 1/2 slope. This one's going to have a negative 1/3 slope, so it's going to be even shallower. This one's going to have a 2/3, negative 2/3 slope, so it's going to be a little steeper, but not quite 1. That was closer to 1. All right, this one's going to have a negative 3. Let's see, negative 3 over negative 1 is going to be a negative 3 slope, because it's going to be positive 3 over negative 1. Yep, so it's going to be negative 3 slope, so we're going to make that one pretty steep. And then this one is going to be a negative 3 over negative 2, so it's going to be about negative 3/2, so it's going to be a little bit shallower. We're going to come over here, and we can just fill in these ones. That's going to be a pretty shallow one because it's a 1/3, positive 1/3. Yeah. And then this one is going to be steeper because it's 3 over 1. This one's going to be shallower because it's 3 over 2. Okay, I think we filled them all out. Whew! It only took 9 minutes. All right, so here's our slope field. So in example 2, we made a slope field. So we want to start at the point 0, negative 3 and follow the flow of the slopes to sketch the solution curve containing that point. Now, we're not going to be touching each of these points, right? Because our function doesn't necessarily touch every single point. So we're going to start at negative 0, -3. So 0, -3, 1, 2, 3. And we're going to just follow the flow of the slopes. Oh, oh my gosh, I forgot to put in some slopes. What happens when x equals 0? What happens when x equals 0? Well, all of the slopes are equal to 0 because 0 divided by anything is 0. Okay, so there we go. All right, so we're going to follow the flow. So we're starting here, and we've got this slope of 0, and then we're going to kind of, I don't think I'm going to use the highlighter. I'll use this one. This has a 0 slope, and then that's kind of got a steeper slope, and then it kind of gets steeper and steeper, and then it gets right here, and it doesn't have to, it's not defined right there, right? And so we're just trying to draw our lines so they're parallel, to those slopes. So I feel like I didn't do a great job over here. Maybe it's my slope field line, I think, that's a little off. It should be more parallel to that. But that gives you an idea of what that would look like. So, like I said, the graph should be parallel to the slope. And it has to represent a function. So the biggest mistake that students make is that you just keep going. So you keep thinking like, oh, I'm just going to keep going. But what happens if you keep going up here? Well, now it's not a function anymore because it's like becoming a circle. And so the vertical line test would be failed very miserably if you put anything there. So you just have to stop when you realize that you're doubling back. The function has the largest possible open interval given the point. So we can go as far as we can go until it stops making a function. Okay, sketch the solution curve passing through -1, 1. Okay, so -1, 1. So this one, we're going to be kind of parallel. So it passes through there, so it's going to be parallel to that, to this slope right here. And then we're going to kind of go and look and see what happens. Let's see, so it should flatten out there. And then it should kind of get steep again and then come back down. So just about like that. And again, it can't go any farther because it wouldn't be a function. So the question is, what type of differential equation do we seem to be, what type of graph do we seem to be getting out of this differential equation? And we're getting semicircles.